That's the question. Anybody officially occupied period 6 on Friday? What is the nature of your period 6 occupation?
I won't be able to make it for period 6.
Why? You have to work? Anybody else? Okay.
What time is period 6?
Right after this gang. 3:15.
I have class.
Okay. How many of you in total? Okay. Well, let me explain what I've got in mind. For quiz 2, what I would like to do is to give you quiz 2 at the conclusion of Friday's lecture class, and then give you up to 2 hours to deal with it. Take it with you, work on it, and bring it back to my office. The only requirement would be that you get it back to me, my office, by 5:30, 6 o'clock, something like that. So regarding you folks who have indicated a conflict, I'm curious if you'd be able to do this in some fashion. If not, possibly I can make a different arrangement with you folks, which I don't mind at all, to give us a chance to expedite matters, get more material laid down, and in essence give you much more time to work on quiz 2.
Does that imply it's going to be a much harder quiz?
It does not? No. Doesn't mean that at all. In fact, in this venue, you could work together. I wouldn't care. My concern is that you learn. That's what I care about. If a quiz would be harder, no. Okay. Well, you folks who indicate a conflict, think about the possibility of maybe me doing this, but I make a different arrangement with you folks. Okay? I could, for example, if it'd be possible for you folks to pick up the quiz, say, sometime early Friday, and turn it in period 5 when you come up for lecture. I don't care. Something like that. Maybe just pick it up Thursday. Bring it back Friday. I don't care. I'm curious about your learning. And I'm also concerned about the compact nature of this rush course and not being able to, in adequate time, present the material which is needed to be presented. Well, think about it if you will, and I'll think more about this and discuss it further tomorrow. Now then, polyprotic acids. 3 subcategories. Yesterday we laid foundation for understanding subcategory number 1, where the parent acid is strong and molecular. The most common example of which is, once again, sulfuric acid. First ionization, 100%. Second ionization, which involves the reaction of hydrogen sulfate ion with water, is subject to equilibrium control. But, based on what we've already considered, we recognize Ka for hydrogen sulfate ion, 1.2 times 10 to the minus 2, is a number which is 120,000 times bigger than 1.0 times 10 to the minus 7. Upshot, without making solutions of hydrogen sulfate ion particularly dilute, hydrogen sulfate ion to 2 sig-figs can ionize 100%. So, if we have a fairly dilute solution of sulfuric acid, you can immediately gee-whiz the hydronium ion concentration for the solution as being what value? You're looking at the M sub I label on the bottle. The solution is, say, 0.00010 molar. 10,000th molar. That's pretty dilute. What do you think the hydronium ion molarity is for that solution?
Plus X.
I don't want to hear X's, I want to know the value. 0.0002. It'll be twice m sub I. You see why? The first ionization reaction goes 100%. That establishes minimum hydronium ion molarity for this solution of m sub I. And now, with Ka hydrogen sulfate ion being a large value as far as Kas for weak acids are concerned, and the solution being quite dilute, that second ionization reaction is also going to go 100%. Well then, that puts another 0.00010 moles per liter of hydronium ion into the pot, so you add them up. There's the hydronium ion molarity, twice m sub I. I trust you recognize that the maximum hydronium ion molarity for any sulfuric acid solution in relation to m sub I is twice m sub I. Has to be. Because now you've taken both protons from the hydrogen from the sulfuric acid molecule. Now, well, we could extend that one further consideration. We're talking about a really, really, really dilute sulfuric acid solution. Not only will the hydronium ion concentration from the sulfuric acid solute be twice m sub I, now Kw would get into the action. Even more fun. But we've already laid foundation for understanding that. But regarding ionization of the sulfuric acid molecule itself, for a fairly dilute solution where Kw will not yet factor in, you can expect hydronium ion molarity to be twice m sub I, or at least something that's pretty close to twice m sub I. Now then, specifically for the 1,000th molar sulfuric acid solution, which we considered in brief yesterday, and along the way recognized these properties for any sulfuric acid solution, provided it's not so concentrated that solute sulfuric acid itself doesn't ionize it entirely. You have to be 12 molar or greater before that condition is going to set in. And we're not going to deal with any such sulfuric acid solutions. So, the arithmetic that you must do to wrestle with this is dealing with Ka for hydrogen sulfate ion. There it is chemically. For this solution, since the hydronium ion molarity is m sub I plus sulfate, there's the hydronium ion molarity, sulfate, and the hydrogen sulfate ion molarity is m sub I minus sulfate. Because m sub I is the sum of hydrogen sulfate molarity plus sulfate molarity. So what are we going to do to solve this? Quadratic if you expand it algebraically, but you know I'm not doing anything with any quadratic stuff. I'm going to think about percent ionization. And I'm going to take advantage of the information which we have just finished discussing. Ka for hydrogen sulfate ion is a fairly large number. And this solution is fairly dilute. So we can expect, before we do any arithmetic, we can well expect that the ionization extent of hydrogen sulfate ion is considerably appreciable. But from an arithmetic approach standpoint, when you're going to speculate on percent ionization, what value should you speculate on first if you don't have any reason to the contrary? 50%. Why 50%? You can see why. Because the molarity of this stuff and the molarity of this stuff will be equal, because half of this converted to this. And at 50% ionization, the hydronium ion concentration will be this. So we'll start with the 50% ionization and see that 1.5 times 10 to the minus 3 is considerably smaller than 1.2 times 10 to the minus 2. We haven't yet done anything fancy. In fact, you don't have to do anything fancy at all with problems like these, if you understand the chemistry, to realize that the true percent ionization compares how to 50%. It's got to be a lot bigger, because this is way too small, right? So if I try 80%, you see how to play the game. You get 7.2 times 10 to the minus 3. That's still too small. 90% gives me 1.7 times 10 to the minus 2, which is now bigger than Ka. But now I've got this percent or extent of ionization boxed as something greater than 80% but less than 90%. 87% does it. You do the arithmetic to prove it to yourself. And when you do these proofs, be sure you always pay attention to significant figures in order to get the correct percent or extent of ionization. Question 1848 is talking about how hydronium ion molarity for a sulfuric acid solution compares to sulfate ion molarity for the sulfuric acid solution if we're at the opposite extremes for concentration. Very concentrated, but sulfuric acid molecule still 100% ionized, or very dilute. Well, if we're very concentrated, to what extent will the second ionization proceed? If we're very concentrated. Will the second ionization proceed to a large extent or small extent if m sub I is a big number? It's like 6 molar. Small, right? The larger is m sub I, the more concentrated the solution. So the smaller is extent or percent of ionization of any species as a consequence of reaction with water. And that's what Ka2 for sulfuric acid corresponds to. Which means that's what the hydrogen sulfate ion reaction with water corresponds to. So in that case, the solution is quite concentrated, but solute sulfuric acid is still ionized 100%. And any molarity, to my knowledge, less than 12 molar, this will apply. How will these molarities compare? First ionization going 100%. Second ionization, which is the way we get this stuff in the pot, is going only to a very small extent. So how will these molarities compare? How do they compare? This will be bigger. A lot bigger? You're damn right. Okay? Now let's take the very dilute solution. Again, the concentration opposite, so to speak, of the very concentrated solution. We just finished discussing this. How will these molarities now compare? The first reaction creates a hydronium ion molarity, that's m sub I. Now the second reaction is also going on the order of 100% because the solution is very dilute. And for the second reaction, the hydrogen sulfate ion molarity starts out at m sub I. But it's going 100%, practically speaking. So that makes a sulfate ion molarity, which compares how to m sub I? Same. And it winds up making a solution hydronium ion molarity, which compares how to m sub I? Double. Isn't that what we just talked about? For very dilute solution, we said, hey, you can all immediately gee whiz the hydronium ion molarity to be twice m sub I. Here's such a case. So, bingo. Now, in which of these solutions is the hydronium ion molarity considerably greater? I ask this question because I don't want you to get tangled up by this language. I want you to understand it. The first one, isn't it? It's concentrated, isn't it? It's got to have a higher hydronium ion molarity. Now then, I'll ask another question. What is the maximum molarity for sulfate ion in a sulfuric acid solution? With sulfuric acid being the only solute. The maximum molarity of sulfate ion in any sulfuric acid solution. With sulfate, with hydrogen sulfate, with sulfuric acid being the only solute. I want the value, the number, the maximum sulfate ion molarity. Be surprising what you can gather about these solutions if you think about and understand the chemistry. Well, first of all, let's go back to these two solutions. In this solution, very concentrated one, the hydronium ion molarity is considerably greater than sulfate ion. In this solution, the very dilute one, the hydronium ion molarity and sulfate ion molarities compare like this. In which of these solutions is the sulfate ion molarity greater? Baloney! You can't get something for nothing. In the more concentrated solution, the sulfate ion molarity is guaranteed to be larger. So what is this maximum sulfate ion molarity? The numbers on the board. It's on the top slate. It's about the left middle of the top slate. Because, let's put the parts together. If the solution is quite concentrated, okay? That's the solution we're talking about, where the sulfate ion molarity will be considerably greater than in the dilute solution. If the solution is quite concentrated, how does the molarity of hydronium ion compare to the molarity of hydrogen sulfate ion? First ionization reaction goes 100%. Second ionization reaction is going almost nothing, right? It's very concentrated. So hydronium ion molarity compared to the hydrogen sulfate ion molarity, what is it? Equal. They're about the same, aren't they? Wonderful. Zap. Bingo. There's your max sulfate ion molarity. If you're puzzled by this, sit down, write it out, and it's going to say, oh, and you're going to, oh my! Well, I understand that part. You're not having the oh my reaction yet, but I'm programming you to do just that. You've got to create an environment for yourself in which the chemistry of the system screams at you. Because that's what this is all about. To understand the chemistry. Because the arithmetic all follows. But if you try to do this with arithmetic without paying attention to the chemistry, you lose. You have no chance. Nothing. Zero. All right, 1849. Let's stipulate that the hydronium ion molarity for a particular sulfuric acid solution is 4 times the sulfate ion molarity. For this solution, what's the hydronium ion molarity? Well, let's put together the parts that we have already made ourselves aware of. For any sulfuric acid solution, hydronium ion molarity is M sub I plus sulfate, which is equal to the hydrogen sulfate ion molarity plus twice sulfate. Okay so far? And M sub I is also the hydrogen sulfate ion molarity added to the sulfate ion molarity. All I've done is restated those properties of a sulfuric acid solution with which we have already established and made ourselves familiar. All right? So, if I have said the hydronium ion molarity, whoop, here it is. Let's not get this time up with this. If I've said the hydronium ion molarity is 4 sulfate ions, okay, and hydronium ion is M sub I plus sulfate, then 4 sulfates, which is equivalent to hydronium ion molarity, is M sub I plus sulfate. So M sub I is 3 sulfates, isn't it? Okay. Well, then hydronium ion molarity, pardon me, then the hydrogen sulfate ion molarity is twice sulfate. Is that okay? Is this not true? Right? And we've said that this is equal to 3 of these. Right? Well, if 3 of these is equal to that, watch out, this is really tough now. X. I'm going to take X away from 3X. That gives me 2X equal to that. And X is sulfate ion. And if I see you doing this, writing down X's, I get out my thwacker. As soon as you start turning this stuff into this XY stuff, you're going to get yourself lost. Because you'll put yourself in great risk of losing the chemistry of the system. Once you do that, the game is over. Well, we got all we need now. Here's Ka. Sulfate ion up here, equilibrium molarity of hydrogen sulfate ion down here, which we've established to be twice sulfate ion. So there it is. So the hydronium ion molarity is twice Ka. Done. And if you wish, you can get, obviously, the sulfate ion molarity as well as the hydrogen sulfate ion molarity. Now we go to the second subcategory, or category, of polyprotic Bronsted acids. The parent acid, parent polyprotic acid, is molecular but weak, as opposed to molecular and strong like sulfuric acid. Arithmetically, you will see this is the easiest case with which to deal. Examples are a bunch of examples in the acid-base table on the info sheet. There's also an acid-base table contained in Chem Notes proper, but not using that one anymore, because the info sheet has got a lot more information in it. Phosphoric acid, oxalic acid, H2S, hydrated CO2, H2PO4 minus, all kinds of polyprotic acids in that table. Hydrated metal ions, a bunch of polyprotic acids in our table. But now the specific type of polyprotic acid with which we are concerned is that for the parent acid being weak and molecular. Now, in the notes, the hydrated CO2 system is analyzed in detail. So let's pick a parallel system, rather than simply write down again what's in the notes. Let's try H2S solution, specifically 10th molar to 2 sig figs, and pose two questions. For 10th molar H2S solution, what's the hydronium ion molarity? How do we get it? And what's the sulfide ion molarity? Now, before we do any arithmetic, can we say that the hydronium ion molarity will be small? When I say small, I mean a number that's a lot smaller than m sub I. Can we say that? On what basis can we say that? What we're now trying to do, because we're going to do this extensively in the next chapter, is to have you get a strong feel for the meaning of a K value. Okay? Is it fair to say, for this solution, before doing any calculation, that whatever the hydronium ion molarity is, it's got to be a good deal smaller than 0.10 molar? Why is that a fair statement? Well, tell me more about this weak acid.
Ka is small.
Ka is a small number, 1.1 times 10 to the minus 7. So it's already telling us whatever the ionization extent of H2S is in this solution, it ain't going to be a whole lot. Now then, how will the hydronium ion molarity compare to the sulfide ion molarity? The answer to that ought to be eminently obvious. What do you know about the base strength of sulfide ion? You looking at the acid-base table? Damn strong base, isn't it? Stronger than hydroxide ion. Sulfide ion is such a strong base that it reacts with water to an extent of 100%, practically speaking. So I repeat the question. For this solution, how will the hydronium ion molarity compare to the sulfide ion molarity? You know the hydronium ion molarity is not going to be a big value. But how will this value for the hydronium ion molarity compare to the sulfide ion molarity? It will be enormously larger. The sulfide ion is a base which reacts with water 100%. And this is an acidic solution. All right? Now let's approach the equilibria that are under consideration. Here's the equilibrium reaction, which corresponds to Ka1 for H2S. Here it is for Ka2H2S. Language, this again, K value for this first reaction is Ka1 for H2S. That's 1.1 times 10 to the minus 7, pulling it right off the acid base table. And for 2, K is Ka2 for H2S, which is Ka for HS minus. And there's a value for this on the table. It's on the order of 1 times 10 to the minus 19. Now, you see this means approximately 1 times 10 to the minus 19. Why do you think that this value is reported as an approximate value rather than as an accurate value? Do you think it's easy to reliably measure a K value that's that tiny? You know what kind of concentrations you're talking about to get K values like that? I mean, that's damn tiny. Awful tough to make these measurements with a particular degree of accuracy, or with any particular degree of accuracy. All right? Now then, next question. Ka1, Ka2. This number is a hell of a lot bigger than this number. For this comparison, this number is only 1 trillion times bigger than this number. Only 1 trillion. Ha ha ha. Why is that? The same would apply to the sulfuric acid solution. When we get to chapter 21, I'll show you how to calculate a Ka value for sulfuric acid. All we can say for now is that whatever it is, it's a damn big number. For any polyprotic molecular Bronsted acid, because that's what we're talking about. Why is Ka1 always going to be a number that's a whole lot bigger than Ka2? Are you with us today, Coulomb? You better be with us all the time, Coulomb. This reaction involves taking H plus from a neutral entity, H2S molecule. But this reaction says, in order to go left to right, I have to take H plus away from this thing. You think it's easy to take H plus away from this thing? Well, we've already recognized this is a potent base, isn't it? That means it's an extreme H plus hog. Well, why is this an extreme H plus hog?
The charge density.
Charge density. What kind of charge density?
Largely negative.
Negative charge density, you betcha. That's a monatomic species with a charge of -2. That corresponds to a significant negative charge density. And if you're going to make equilibrium reaction number 2 go left to right as written, you got to take H plus away from this thing with this large negative charge density. Coulombically speaking, that's damn tough to do. And whenever you take any molecule, because we're talking about molecules now, specific molecules, which are polyprotic Bronsted acid, but they're still molecules. After Ka1, you will now be forced to extract H plus from something that's minus. And that ain't easy to do. What can you tell me about the positive charge density of H plus? How do you think the positive charge density of H plus? Right here. Compares to the positive charge density of this thing. Al3 plus versus H plus. I want a comparison of the positive charge densities of these two species. Which has by far the greater positive charge density? Which is it? Seems like there's a rather significant degree of uncertainty hovering over the heads of our gathering here. Al is 3 plus. Is positive charge density of Al plus 3 greater than that of H plus? How many say yes? I got a half a yes back there. How many say that the positive charge density of H plus makes the positive charge density on Al plus 3 look like nothing? All right, tell me why. You voted twice. That's all right. You get a double participation count. Why is that true? I'm listening.
Aluminum has 13 protons in its nucleus, but it also has, like the neutral atom has 13 electrons. So it has 10 electrons in that ion. And hydrogen only has one.
Hydrogen? Go ahead. Go on.
Ion has only one proton, so its surface area.
Wait a minute. It has one proton and what else?
Nothing.
That's right. Do you know what happens to size shrink when you take the hydrogen atom and take away from it its only electron? Whoop! It collapses to a nucleus. And you learn in 2045. The size of any atom is enormous compared to the size of its nucleus. Because it's the electrons, which are not in the nucleus, that define the size of the thing. Particularly the highest S value, the highest N value S electrons, right? Hey, you got a positive charge on this damn tiny thing called a nucleus. By the positive charge density of that is enormous, which accounts for why H plus makes bonds to water molecules. And that's why when I see a textbook who has the nerve to write this on their pages, no, flunk. I'm not accepting this junk. Yeah, from a notation standpoint, that's easier. From a chemistry standpoint, that stinks. Now, this is chemistry, damn it. And I'm not having that junk in the class. I'm not having any textbook in here which makes statements that are contrary to the fundamental principles of this great grand science. No way. One time, a number of years ago, Martin Silberberg himself came here. Are you still using the Silberberg text for 2045? Okay. Okay. He asked if anybody wanted to talk to him after we had a general meeting. I said, yeah, I'll be glad to talk to you about your book. After about 1 hour in my office, he's backing up from me because I had just murdered his book. And then comes the damnedest thing of all this. He invited me to supply him with constructive criticism comments to improve his book. I spent a lot of time on this. I sent him a whole bunch of stuff electronically because he gave me his email address. How much of what I sent him did he use?
0.
You know what he used? He had a picture in the chapter we talked about gases and gas laws, okay, of a gas pressure gauge. Like 0 atmospheres, 1 atmosphere, 2 atmospheres, 3 atmospheres, 4 atmospheres, okay? And with this picture of the gas pressure gauge, he had the needle on the gauge doing this, and the problem was about a gas system with a pressure of 1 atmosphere. So he fixed that. And that's all he did. And I said, you stupid son of a bitch. I mean it. You stupid son of a bitch. I mean, that showed me how interested he was in improving his presentation of chemistry. All the OH minus crap and all this H plus, that all stayed. I said, that's it. One more book for the fireplace. I'm not having that junk. But then, since that time, I don't use any of those. General chemistry books are atrocities. A dedicated student can learn organic chemistry from today's organic textbooks. They're quite well written, and it almost makes no difference what author. Analytical chemistry. If you get the analytical chemistry text by Daniel Harris, which I think some of the instructors here use, that's a great book. A lot of what I do with acid-base chemistry comes from Harris's analytical book. PChem books. There's a big variation in quality of PChem books. Because some of these physical chemists get themselves immersed in math and lose the chemistry. Now, I'm not having that either. But in the main, the junky chemistry textbooks are the ones written for first-year students. The most important audience. It's the largest, as we've already said, and the most impressionable. And they're the ones that get the junk. No, I'm not having that. All right, here we go with this. Because of this, it is true that hydronium ion molarity for this solution, or any water solution of a polyprotic weak molecular acid, is calculable from the first ionization reaction. That's all. You don't have to pay attention to the second one. You don't have to pay attention to the second one. It's too small. It doesn't go anyplace. We're going to prove this in a moment. Well, that means for this solution, since Ka1 is 1.1 times 10 to the minus 7, if I put in 1.1 times 10 to the minus 7 at an m sub bi value of 0.10, I'm in essence taking the square root of 1.0 times 10 to the minus 8. So there's the hydronium ion molarity. All right? What's the sulfide ion molarity? Well, I think you recognize at a glance that if we want a value for the sulfide ion molarity, we have to look at Ka2. Because there's only equilibrium that's got sulfide ion in it. So all right, 1 times 10 to the minus 19 is equal to this times this over this. Okay? And if it is true that we only need to consider the first ionization reaction, because the second ionization reaction goes, practically speaking, no place, for this H2S solution, for any H2S solution, how will the molarity of hydronium ion at equilibrium for the system compare to the molarity of HS minus at equilibrium for the system? How do these values compare? How do they compare? They're the same, aren't they? Because the second reaction isn't going any place. Well, then there's your sulfide ion molarity. It's Ka2. And that statement applies to each and every water solution of a weak polyprotic molecular Bronsted acid. The species produced by double proton loss by the parent molecule has a concentration which is always equal to Ka2. This gives you an idea why the arithmetic for this situation is easy. You pay attention to Ka1 to get hydronium ion, don't have to do anything with Ka2. And if you want the molarity of other species in the system, you take advantage of knowing that the molarity of the species produced by double proton loss by the parent acid, because H2S loses 2 H pluses, its sulfide ion, is always equal to Ka2. Now then, students in the past have said, how can I know this? How can I know that Ka2 makes no contribution? Well, let's take a look at a proof. Okay? Now, the system I want to look at will be a system that's analyzed in the notes, hydrated CO2. Now, you can't make hydrated CO2 get a molarity in water unless you have it under pressure that is above about this molarity. The CO2, as you know, because it's not soluble and because it's a gas at NLC, because it's a gas at NLC and not polar, is not very soluble in water. I repeat my directive again. If you don't believe this, go get yourself a can of beer, warm it up, shake the hell out of it, and then open it. Then you'll believe it. Out comes the CO2. And you will wreck the good beer. Well, maybe it's not a good beer. I don't know. Maybe it's that junk they make in Colorado. Sewers, is that what it's called? Sewers? Oh, Coors. I call it sewers. It's got this flavor. I get more taste out of my cup of tea. Okay? We're at least getting now some good beers made in this country by none of the major breweries. By all these people who are making this kind of special beer, that kind of special beer. A lot of good beers there. Because they're like European beers. They got some bang taste to them. And power. You get a beer that's 9-10%. Hey, that's a beer. On we go. Now then, hydrated CO2. Based on what we've said, let's calculate the hydronium ion molarity for this hydrated CO2 solution, which is Ka1 times the square root of Ka1 times m sub I. There's m sub I. And for H2CO3, okay, let's put the values down here. K1 is, as we've written over there, 4.2 times 10 to the minus 7. And Ka2, which is equal to Ka for bicarb ion. I got to check these values because I upgraded the information in this table. 4.7 times 10 to the minus 11. I used to have it as 4.8, but that's still pretty close. You know, but as better information comes along from more recent and better made measurements, I try to incorporate that stuff into this information which we use. Okay? Now then, here again, Ka1 is a lot bigger than Ka2, but hardly like this. Okay? Here, a trillion difference. So do you accept my statement that if Ka2 was going to make any contribution to the hydronium ion molarity for a solution of a weak molecular polyprotic acid, it would be much more likely in this solution than in that solution? Because here Ka2 is a whole lot bigger than Ka1. Ka2 here, and here Ka2 is not nearly as smaller, not nearly so small. It's not as much. Damn it! This is not nearly as greater than this as the ratio there. Let's try it that way. Sometimes I have to iron my tongue. It's twisted up. Okay. Now then, here's what we got. Now, if Ka2 for the hydrated CO2 solution makes a contribution to hydronium ion, well, then we got to look at Ka2. So we'll do that. Here's Ka2. And if Ka2 makes a measurable concentration, a measurable increase in hydronium ion concentration, then these concentrations will not be the same, will they? Which one will be larger? This or this? Which molarity will be larger? This or this? If Ka2 makes a contribution to hydronium ion molarity. This has got to be larger. Because what I'm doing now is making hydronium ion at the expense of consuming hydrogen carbonate ion. Okay? Well then, for this solution, based on what we learned up here, based on square root of Ka1 times m sub I, we get a hydronium ion molarity of 6.5 times 10 to the minus 5. And if the second reaction doesn't go, down here, if this reaction isn't going any place, okay, then the bicarb molarity in the solution remains at 6.5 times 10 to the minus 5, just like the hydronium ion molarity. Because from the first reaction, the molarity of this and the molarity of hydronium ion are the same. Now we're considering the possibility of those molarities not winding up being the same because some of the bicarb converts to hydronium ion. Well, all right. Let's make a concentration increase for hydronium ion. If there is a contribution of a measurable nature to the hydronium ion concentration by Ka2, which is this for the hydrated CO2. Then the hydronium ion concentration got to increase. Fair enough? What is the minimum increase that this value can experience? You got two sig figs here. By what's the smallest increment by which this can increase measurably? What will it become? What will be the new value? Tell me what it is. Right? 6.6. You got to let these numbers talk to you. Okay. If there's any contribution at all of a measurable nature to the hydronium ion molarity, then the hydronium ion molarity has got to become at least this, or something bigger. Okay? But it's got to become at least this. Otherwise it stays at this. Fair enough? Well then, if the hydronium ion molarity would increase from this value to this value because of this reaction, then what will be the equilibrium molarity of this? Because after the first reaction, this had a molarity equal to this. Okay? So what will this become? If this becomes the equilibrium molarity for hydronium ion, then what will be the corresponding equilibrium molarity for bicarb? It'll be this less 0.1 times 10 to the minus 5, won't it? Because that will be how much of that became this. Okay? So this would become 6.6 times 10 to the minus 5. And this would become 6.4 times 10 to the minus 5. Okay? And this would be the carbonate ion molarity. All right? Well, tell me. Because if this chemistry happens as we have so described, and this reaction creates a hydronium ion molarity of 6.6 times 10 to the minus 5 by contributing 0.1 times 10 to the minus 5 to the hydronium ion molarity. Okay, so far? What will the molarity of this be? What will the molarity of this be? What will it be? 0.1 times 10 to the minus 5. Won't it? Or 1 times 10 to the minus 6 if you want to write it that way. Okay? Right? Isn't that how much we increased the hydronium ion molarity? Because we used up 0.1 times 10 to the minus 5 moles per liter of this stuff to make 0.1 times 10 to the minus 5 moles per liter of hydronium ion and 0.1 times 10 to the minus 5 moles per liter of carbonate ion. Right? The stoichiometry just tells you that. Now the net hydronium ion molarity will be the sum of what we got from the first reaction plus the second reaction. So now we're speculating on the smallest possible increase in the hydronium ion molarity resulting from a measurable contribution to the hydronium ion molarity by this reaction, or the ionization of bicarb ion if you want to say it that way. All right? Well, let's put this in here. Because all of this combination of terms for this system has got to equal what number? What number must this combination of terms equal for this system? Got to equal this, doesn't it? Does this come close to this? These values are about the same. And the carbonate ion is 1 times 10 to the minus 6. How does 1 times 10 to the minus 6 compare to 4.7 times 10 to the minus 11? One hell of a lot bigger. So is there any contribution by the second reaction? Not at all, none, zero, zip, because what we in fact have proved is that whatever the equilibrium molarity is of carbonate ion, it's a whole lot smaller than this. What is the equilibrium molarity of carbonate ion? There it is. It's Ka2. Just like we said up here. Remember? When you take a weak molecular polyprotic acid By double proton loss, you will have a species whose molarity is always equal to Ka2. That's what we got again. Okay. And now, we're ready to have the greatest fun. Shouldn't leave before the greatest fun. Here comes the greatest fun. We'll take the example that's considered in the chem notes. Okay? And now we're going to create some notation so I don't have to spend too much time writing. So I don't have to keep writing these long, correct formulas all the time. Notation standpoint, this represents this represents this represents this.
Is that iron OH2 or I can't see those.
No, those are water molecules in there.
Okay.
Okay, now then. Some information. Some of you may get far enough along in 46L to deal with some of this chemistry. It's in assignment 10. That's a pale violet color. This is yellow-orange. No. Yellow-brown. As is this. Which color do you think is more intense? Pale violet or yellow brown? Pale violet. Right. Now then. I found a new value for this Ka. I had 4.0 times 10 to minus 3, but now I've incorporated 6.0 times 10 to minus 3 from this latest bag of information, and that's the value you'll see for Ka1 for this character in our acid base table. Okay. Okay so far? Oh. There now may be a better value for this K, but I haven't taken time to look for it yet. Now, what is the main difference from a quantitative standpoint that you see between this system and, for example, that system? Do you see that there's not much difference here between Ka1 and Ka2 like what we've seen previously? Not much difference here. So why is it that for this system, the hydrated metal ion system, Ka2 has a magnitude which is rather close to Ka1? You still here, Coulomb? Remember the problem we were fighting here? The problem fighting here is when you're going to pull the second H plus from the parent molecule, you are in fact pulling that H plus from a negative species. And the stronger the basic nature of that negative species, the more difficult it is to extract that H plus. But if I start with a multiply charged positive ion, do you think coulombically I lose H plus coulombically, I lose H plus favorably? Because I'm reducing the negative charge concentration on this thing. Same here. So here I get a coulombic boost to these ionization processes. Over there for the second ionization process I get a coulombic restriction. Here I get a coulombic boost. That accounts for why these Ka values are kind of close. Now then, what is the upshot of the closeness of these Ka values when it comes to determination of hydronium ion concentration, say for this solution?
You have to consider both reactions.
We'll have to consider both reactions now? You're damn right. And there comes the problem from a calculation standpoint. There comes the additional degree of complexity. Because if both of these reactions are contributing measurably to the hydronium ion concentration, and as yet I have no knowledge as to the extent of these reactions, the only thing I know for sure is the extent of this has got to be greater than the extent of this. But if the extent of this is appreciable, hey, then I got to get a handle on the extents of each reaction. Well, how many unknowns does that give me? Well, I want to get this, but I won't know what it is yet. I want to get this, I don't know what that is yet, because these molarities won't be equal. X squared over m sub I minus x won't apply to this. And if I don't know this, then I don't know this. So, I don't know this at equilibrium. This is a label on the bottle. I don't know this at equilibrium. 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 How many unknowns I got? 4. How many equations have I got so far? 2. Can I solve this? Not yet. But can we solve it? Well, of course we can solve it. In order to solve such a system, you learned this in algebra class, if I got 4 unknowns, I've got to have at least 4 simultaneous independent equations composed of those same 4 unknowns. Then I can solve it. Well, let's write an additional equation based on what we've already learned. That's called material balance. Let's call it Mb iron. The label on the bottle says I have a molarity of dissolved iron, the sum total of which has got to be 0.010. If I add up the molarities of all the forms of iron in solution, I got to get 0.010. Because that's how many moles of iron per liter I put into the system. So I can immediately write this. Now I'm in position to solve for one of my unknowns, any one of these iron forms, any molarity of any of these iron forms, in terms of the other two. If I want to solve it for this, then it's 0.010 less this, less this. If I want to solve it for this, it's 0.10 less this, blah, blah, blah. Okay? But I'm still short one equation. From where can I get this other equation? From this. The principle of electroneutrality. On what does the principle of electroneutrality depend, Professor Coulomb? In any bulk chemical system containing charged particles, how must total moles of plus compare to total moles of minus? They gotta be equal. Otherwise, the system would be grossly unstable from an electric standpoint or electronic standpoint. Story? Some of you heard this yesterday. When I taught 46 Lab, here when I was a TA, I came starting here in 67. You know, back in ancient history, as far as you're concerned. We had TV then. Calculators were just coming up. Internet, what the hell was that? Nobody knew anything about that. Computers on everybody's desk, huh? In assignment 2, 46L, one of my students, well, like all the students, was faced with the task of doing a flame test for the sodium ion. Just like you all did in assignment 2. And a flame test for calcium ion, assignment 3, blah, 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 okay? This student, after searching about the shelves in the laboratory for a while, became very upset and frustrated. I inquired, what's going on? What's the problem? I can't find a bottle that just got sodium ion in it. He said, do a sodium ion flame test. So the student was searching for this bottle that had on a label Na+ and nothing else. So I told him a story. You know me, I like to tell stories. I said, guess what? If a collection of Na+ were stable, given that I make Na+ by this reaction, then the electrons themselves would be stable. Because if I can bottle up the Na+, then I can bottle up the other product of this reaction, the electrons. So I'd open up a store on the corner. Horvath Electron Store. I put all my electrons in a bottle. Boy, I mean, you put one hell of a bunch of electrons in the bottle because they ain't very big. Okay? And I'd sell everybody these bottles of electrons. And then you could go home, take a funnel and jam it in the socket in the wall and pour in the bottles of electrons. The electrons would flow through the circuits, and the radio would radiate, and the toaster would toasterate, and the television would televise, and you could call up GRU and say, go to hell, I don't need you anymore. Unfortunately, we can't do that. Because when you try to concentrate particles of like charge with each other, you get something called an explosion. Because they repel each other strongly. Ain't that right, Professor Coulomb? Upon that depends the principle of electroneutrality. Total moles plus must equal total moles minus. And from that, for this system, we can write a charge balance equation and set it equal to a charge sum. So what I'm going to do now is to write the charge balance equation for this system. I'm going to set it equal to its corresponding charge sum and let you think about it. Here we go. Charge sum equals 3 times the molarity of Fe3 plus 2 times the molarity of Fe2 plus the molarity of Fe plus the molarity of hydronium ion equal to the molarity of hydroxide ion plus the molarity of nitrate ion. Notice that the terms which I have written involve every positive and negative species in the pot. All the ions in the pot are here represented. And when I sum up all the plus molarities, which is equal to the sum total of all the minus molarities, I will get 0.030. Do you see all this? Think about it. We'll pick it up from this point tomorrow.